Welcome to this biochemistry lecture on the primary structure of proteins. So structure comes in 4 flavors. There is the primary structure, which is basically the sequence of amino acids in a polypeptide chain, as you might recall, and we'll go over this in a little bit. A peptide, polypeptide, or a protein are all amino acids that are in a long sequence in a chain, kind of like beads on a string. And the primary sequence is the order of the amino acids. Secondary structure is a conformation of amino acids in a localized region, meaning that there are localized features within a protein that are important. The tertiary structure is the overall structure of the protein, the overall three-dimensional layout of the protein. And then there's quaternary structure, which is the structure of more than one polypeptide chain. So we're going to talk about the primary sequence, the primary structure or amino acid sequence of proteins in this lecture. The important bonds in the primary amino acids sequence or structure. The primary one is the peptide bond, and as we've gone over this in other discussions, but if we have 2 amino acids, the carboxy group of one amino acid and the amino group of another amino acid have a condensation reaction, and in that condensation reaction there is water that is produced and the amino acids link together. And what we're going to do is we're just going to keep linking these amino acids together in with this peptide bond in a long chain. Amino acids are very good nucleophiles, but the hydroxyl is a very poor leaving group, and so it's not a very favorable reaction. Thus, enzymes, e.g., ribosomes, are where this needs to occur. So at physiological pH, the peptide bond formation occurs in the ribosome. So when we start doing this, when we number the amino acids, we start numbering at the end of the amino acid where there is a free amine group, and we end it where there's a free carboxyl group. So in this situation, you can see amino acid 1, which happens to be a serine, and then you can see that there's a peptide bond, and then there's another amino acid which happens to be a glycine, and so that's amino acid number 2. Then you can see the peptide bond, and then amino acid 3, which is a tyrosine. You can see a peptide bond, and so on and so forth. An alanine, and then a leucine. And so then, that can go on for small number of peptides up to thousands of amino acids. And the interesting part about this is there is, for every slot, there are 20 options. So for slot number 1, there's 20 options. For slot number 2, there's 20 options. And so this grows pretty quickly. So there are 400 combinations for a dipeptide. There are 8,000 for a tripeptide. For n number of peptides, there's 20 to the nth. And so with 60 amino acids, which is a relatively small amino acids, there's 10 to the 78th possibilities, so which is greater than the number of atoms that exist in the universe. And so there's virtually a infinite number of options that can be formed from this as you get a peptide to a certain length, and that structure is dictated by the sequence, and that structure then dictates the function. So all of this comes back to the sequence of the amino acid. If we want to calculate what that sequence is, generally this day and age we do a sequence of the genes, and then from there we can calculate what the sequence is. We can also use Eggman degradation if we don't know that, or you can use some kind of tandem mass spec if we're going to do that otherwise. So there's 3 ways of naming this. We can go single letter code in this situation. Serine, glycine, tyrosine, alanine, and leucine is SGYAL, or we could do 3-letter codes, which in this case would SER, GLY, TYR, ALA, LEU. So, or you could do the full amino acid name, which will be seroglycyl tyranosyl alanine leucine. So all three exist. Commonly, if they're very large, we just use 1-letter codes, and we'll also use 3-letter codes commonly for things like mutations, naming mutations, which we will talk about later. One thing that we're going to discuss now, which sometimes people put in the tertiary bond section or tertiary structure, is disulfide bonds. I'm going to put it here because this is totally related to the primary amino acid sequence, and it's only one amino acid, cysteines, which form disulfide bonds. It's basically when two sulfur groups form a bond together, and that stabilizes this cross-linkage between the amino acids, stabilizes the protein. The bond is an oxidation of the two cysteines. When you break it apart, usually with DTT, it's a reduction. That's a pretty important point to understand, because that's how sometimes you need to reduce this bond in order to do some biochemistry or molecular biological techniques. And when the two cysteine groups form, it forms a cysteine. C-Y-S-T-I-N-E, not C-Y-S-T-E-I-N-E. That's an important distinction. And this is a moderately strength, low to moderately strength bond. It has energy break of 60 kilocalories per mole with a bond length of 2.05 angstroms. So it's it's fairly low to moderate energy requirements. So keep that in mind. So this is an example. The insulin hormone, the hormone insulin, is an example of a polypeptide, and it's just to give you a couple of examples of how peptides can function. This hormone, we started initially when we started doing for diabetes, when we started doing hormone replacement, we used the pig insulin because it was fairly close as far as amino acid sequence, and therefore it had the same structure and function. And so the idea is generally the amino acid sequence as if they're related, or they have we would call conservative replacements, meaning they're not dramatic. So if they're within the same group or conserved, then amino acid, then they're not going to change. So if you have a glutamic acid and it goes to an aspartic acid, there's not a lot of difference there. That's pretty conserved. Or if you go from a leucine to an isoleucine, or from an alanine to a leucine, you're not going to disrupt the general characteristics of that bond, and it's fairly conserved. Conserved meaning that there's not going to be a huge disruptor. The important points of conserved are size and charge, and sometimes both. So if you put something like if you replace something like an alanine with a tyrosine, that's very large. If you replace a phenylalanine with sorry, that's probably not a great example. A lysine with a glutamic acid, you're talking about a complete differences in charge. Or even if you take glutamic acid and replace it with a glutamine, you're talking about eliminating charge there, and so those kind of changes are not going to be conserved. One other thing that we need to just briefly mention is post-translational modifications. Those are covalent linkages of different functional groups, from as small as phosphorylation up to as large as ubiquitination, which is a large protein, to glycosylation, which are carbohydrates. And in this chart, you'll notice that underneath the description, there are residues, amino acid residues, that these functional groups can be added onto. And they have numerous different functional properties, including changing structure, signaling, any number of things like histones are post-translational modified. Ubiquitination is used for recycling a protein. Glycosylation changes the structure, is also used for cell signaling. Any prenylation, some of these lipid groups can be used to anchor. So there's all kinds of different things. Acetylation and methylation are all used, and hydroxylation are all used in changing structure. So these are very important in those roles. So that's primary primary sequence, primary structure of amino acids and proteins, and we will look forward to seeing you in the next video and lecture.